And batteries, magnets are the same way. Opposite poles attract, right? So dipole means you now have two poles. That's why these are called polar. Because of this difference in electronegativity, and that's a pretty big difference, difference of 1. Because of this difference of electronegativity, this side of the molecule becomes partially negative. And the way we show that, it's a negative, but then it looks like that. It almost looks like an 8 that you don't finish. Some kids tell me it looks like a music note. It's supposed to be like a lowercase sigma is what it's called. This is a partial negative. Partial negative. So if all the negative charges, the electrons, are getting pulled towards the Cl, it should make sense to you that this side, right, this line is like the middle. This side is going to have more negative charges. This side is going to have less negative charges because they're getting yanked that way. So this side has a partial positive charge. These partial charges, partial positive. These partial charges are the reason this thing is called polar, and this arrow is called a dipole moment. So the arrow always points towards the side that's winning the tug of war. Always. So if you have a compound or a molecule, you go to table S, you look up their electronegativity. The one with the higher number, that's the one the arrow is pointing towards. That's where the electrons are getting pulled towards or yanked towards. The other side is going to be partially positive because the electrons are getting pulled away from that. Electrons are negatives. The other way to kind of see this is these dots are also electrons. So if you draw a line right down the middle, how many dots over here? None. But you have 6 over here. So there's more negatives over here, less negatives here. So more negatives means partially negative, and then partially positive means less negatives. The reason it isn't straight up positive negative ions is because this is covalent. These electrons aren't actually all going to Cl. It's just Cl kind of has more of them. I know that's a little confusing, but it isn't transferring like ionic. So these are not ions like Na plus and Cl minus. Like that's ionic. So when you do a dot structure with NaCl, this is +1 -1. These are not the same thing as these. These have that weird symbol. That means partial. These are actual charges because, the Na is getting rid of that. So Na is really a +1 and Cl is a -1 ion. These are not ions. They're partial charges. And I know that's confusing, but we're going to practice it. Questions? Okay. So you just learned everything you need to know about polar. It just gets a little more complicated. That's why I brought the sheet in. Okay. This. Let's take H bonded to an H, or an F bonded to an F. So put these dot structures down under nonpolar. Over here, I don't need to do anything else. There's literally nothing else to put on the board. There's no partial charges. There's no dipole moment. There's no difference in electronegativity. It's 2.2 and 2.2, and F is 4, so 4 and 4. So because everything is balanced and equal sharing, right? So if I draw this line right down the middle again, everything is balanced, equally distributed like we talked about yesterday, sharing equally. That's why it's called nonpolar. It doesn't have a pole. There are no poles here because electronegativity is the same. If there's a difference in electronegativity, you're going to have a pole. If there isn't, no pole. Hence the name, polar and nonpolar. So this is way more complicated. Look at all the stuff we had to label. Here, this is it. There's nothing else to label. All right? Questions? No question. It was just funny how you did that in slow motion. Yeah, no, you're good. Okay, so this is fairly simple because it's 2 atoms, right? So if you have 2 atoms, what if you have more than 2 atoms? Okay, I'm going to put 2 compounds on the board that have more than 2 atoms. And I want you to draw the dot structures, and then I want you to try and imagine or try and determine are they polar or non-polar. So there's very simple molecules that have just 2 atoms, but then there's others with more than 2 atoms. So for example, H2O, and I'll give you another one here. Let's go CH4. So let's start with these 2. Draw the dot structures, and then if you want to talk to someone near you, be my guest, try and figure out are they polar or non-polar and why. Electronegativity plays a role, but I'm going to give you a little hint here. The shape of the molecule dictates the polarity as well. All right, and that's why I brought in the sheet. I think it'll work. We'll find out. You'll be the guinea pigs. I never did it before. And our next lab, you're going to be getting these molecule kits, and you're going to be building things like water and CH4, which is, by the way, it's called methane, natural gas, the biggest component of natural gas. So you're going to be using molecule kits to kind of visualize this, not just do it on paper, and it usually helps. So I'll do this here though for you one time here. Let's see. You gotta stop having these 2-hour delays. We need more school. We should make up the difference Saturday, come in 4 hours. What do you guys think? Yeah, I don't think my wife would too amped up about that.
I think half of us would need to show up.
Maybe sneaky again. Maybe not try to eat.
There you go.
Just give up. Don't give up. Oh, did you do the thing?
Kind of finished, yeah.
You just show me later tomorrow.
Yeah.
Okay. All right. This is what CH4 looks like. This is like a 3-dimensional version. You can't draw like this on paper, obviously. Okay, so on paper, it would kind of look like that for you guys. So imagine it's flat. That's what it would look like. What's in the middle? Well, there's an easy way to figure it out. How many valence electrons does C have? How many? 4. How many does hydrogen have? 1. So these sticks here are bonds. So there's 4 covalent bonds here between C and H. Each hydrogen is the yellow, can only make 1 bond. Carbon can make 4 because it has 4 individual dots. So you put carbon in the middle, and then you put your 4 H's around it. It looks just like that. So that's CH4. Water now looks like this. It's Mickey Mouse. This does not look like Mickey Mouse, I get that. But if I make the circles bigger, right? This is his head and this is his ears. That's what water looks like. And you could draw however you want. It's 3-dimensional, right? You don't have to do it like this. It can be sideways or upside down, whatever. But that's 2 H's and 1 O. How many dots does O have? 6. 2 dots are by themselves. That's the 2 bonds. The other 2 dots, or other 4 dots, are here and here. So I'm going to put it on the board, but I wanted you to have a visual here. Okay? So here's H2O. Here's CH4. The lab that we're going to start tomorrow, you're going to be doing this. So we're going to give you, I say we, Mr. Becker and I are going to give you, I don't know, 10 compounds. and it's just gonna be like your own lab, kind of like we did last time. I don't have anything to copy. You're just gonna write down on paper 10 of these. You're gonna put them together and do the dot structure. You can do the dot structure first and then put them together. But sometimes it's easier if we tell you the colors, like this is oxygen, this hydrogen, this carbon. You can put them together and then figure out the dot structure from there. And then you're gonna do everything we're doing right now. You're gonna say, okay, this one's polar, this one's non-polar, here's why. If it's polar, you gotta draw your dipole moment, like we just did in our notes, the partial charges, the difference in electronegativity. So there's a lot to learn, a lot to do. I use a lab for that because I think it's useful to see these things. All right, it's a visual. Instead of just doing it on paper or on the board, it's kind of hard because you kind of have to imagine a lot, and you can't because you haven't learned enough yet. Anyways, dot structures. So this is how I want you to do oxygen and hydrogen here for water. So there's your dot structure. One H goes here, one H goes here. It cannot be a straight line. I cannot put this H over here or this one up here. Water is called a bent molecule. It has a bend to it. Kind of looks like a right angle. It isn't a right angle, but that's kind of what it looks like. This is not correct. That does not happen. If water looked like this, life wouldn't really work out. Okay, the reason water is bent is the reason water does what it does and why we are mostly water and why water is good for us. If the hydrogen was over here, it would completely change everything. So that's water. Another way to draw it is with the bonds. Okay, these are the exact same thing. These lines represent covalent bonds, which means 2 dots, one from each. Okay, CH4, we have 1, 2, 3, 4. H goes here, H goes here, H goes here, H goes here. So there's my CH4. And again, if I show the bonds, it's carbon with 4 H's surrounding it. Okay. Questions? So if you were confused, a lot of you were, that's fine. Hopefully it makes more sense now. Questions? Again, the lab's going to help with this. Okay. Come on back. Let's play with the sheet. It's a dirty sheet. I use it as like a rag, kind of. In fact, it was under our Christmas tree. In case it leaks. Plus, I think we spray painted some stuff. Alright. So it's not an actual sheet that's used. Anyways, alright, here we go. Alright. Hopefully this makes perfect sense. Alright, we'll try it. Grab that corner. See, grab that corner. Grab that corner. Grab that corner. And back up until you stretch it out. Come on over here. Okay, make it like tight. Okay, good. Alright, good. Now, imagine this is the CH4 molecule. Imagine carbon's in the middle and U4 are hydrogen. Okay. Now. Okay. No, wait. No, you two got to hold on. Come on, stay with me. Hold tight. All right. What's this? No, what structure is this? Water. I'm oxygen, you two are hydrogen. Okay? All right? So I'm trying to give you a better visual besides the molecules. All right? So now you two are hydrogen and now I'm oxygen. All right? Okay, ready? Pull. All right, good. So obviously they can't keep up. All right, now hold that. Hold that. All 4 of you pull at the same time. Okay, good. All right, stop. That worked out well. What's the point? What's the point? We're supposed to figure out which one's polar, which one's non-polar.
Oh, polar, yeah, and then the other one's non-polar.
So when we have 4 corners again, come on, humor me, stay with me. This stuff helps you learn it, trust me. Okay, pull it tight. This reminds me of that parachute thing. Yeah. That, when I was a little kid in grade school, I freaked out about that game so much. It's like my favorite thing in school. I don't know why I liked it so much. What's the point of that game?
It is, you do that when you pull their legs.
But what was the point?
It's like unobstructed.
That was the point?
There's like other.
Wasn't there something you're supposed to put on it too?
You put balls on it.
Yeah, and keep them up or something? I thought that was fun. Anyways, so when you're, go ahead, pull a little bit. When you pull, all right, equally, not one side isn't pulling more than the other, and it's very symmetrical, right? Would you say this looks fairly symmetrical? That's CH4. But when you have 3 atoms, and again, all right, oxygen, what's oxygen's electronegativity? Remember? It's 3.4, okay? And you guys are 2.2. So you don't have to actually pull, but in reality, this is what happens. Oxygen actually pulls both hydrogens because oxygen has a stronger electronegativity. So this is not symmetrical. I'm going to start winning. I was using the analogy of like a boat and water skiers, right? You're both going and water skiers are following. So I'm pulling them, right? And that means there's a pull, so I create a pole. Whereas, you guys said my comment, thanks. When you guys were pulling equally, there are no poles because everything's very symmetrical. So if you turn around and look at the board, if you look at CH4, does it have symmetry on the X and Y axis? Yes, what about water? No. Does it have symmetry at all, really? Not on the X and Y the way I drew it, right? We could kind of slice it in half and then the eaches would be mirror images of each other, sort of. But what I'm trying to use the sheet for, and I thought it was a good example, is that equally distributed. When I had all 4 of you pulling, that was very equal. And does that make sense? Seemed like it made sense to everybody, okay? So on paper, when you draw a dot structure, all right, if you can imagine a sheet or people pulling, if it looks like everybody's pulling equally, it's non-polar. If they're not pulling equally, it's polar. Electronegativity plays a big role, but also the number of atoms surrounding it. So if it's symmetrical or asymmetrical. Is making some sense? I'm just trying to give you something to like visualize or understand than just, you know, the actual numbers and drawing dot structures. All right, let's go back up. That's going to be fun later when I have Tyler and Shane do it. All right. Okay, so that was recording the whole time. Sorry, I was just looking at this here. This is polar, and this is non-polar. And there's just a couple things I want to get down, and then that'll probably be it here. So the reason water is polar, all right, and you can keep writing your notes. I'm obviously out of room here, but the reason water is polar, there's 2 reasons. If we draw lines like a y and x axis, it does not have symmetry. And symmetry is mirror images, right? So if I draw a line down the middle, there's no h over here to balance out that h. There's no h up here. So one thing you can do to determine polarity is if it's asymmetrical. And again, if you have 1 pulling and 2 pulling and it isn't symmetrical, right? So even though the sheet kind of looked like a triangle, equilateral triangles are kind of equal. That's not what this is at all, because oxygen is pulling the electrons this way. And I want you to label that. That's your dipole moment. Oxygen is 3.4, hydrogens are 2.2. So yes, kids want to say, well wait, 2.2 plus 2.2, that's 4.4, that's stronger than 3.4. Yes, but it doesn't work that way. It actually works individually. So oxygen wins this one, oxygen wins this one, so overall oxygen wins. So it's asymmetrical, which means one direction pulls more. I'll try and keep it very simple. Pulls more. So that's due to electronegativity. The asymmetrical part of the molecule allows that to happen. But over here, nonpolar, that means it's symmetrical, and all pulling cancels out. So, when we're talking about one bond, like HCl and then H2, what we had earlier, just 2 atoms, it's a lot easier to see. But when you have molecules like this, it's harder. So this is how we do it. This is how we visualize it. This is how we talk about it. Is it symmetrical? Is it not symmetrical? If it's symmetrical, then everybody cancels out and it's equal. If it's not symmetrical, then one direction is going to win, and that's your dipole moment, and that's where, you know, it pulls more. Last thing with this, in this structure here, oxygen, this side is going to be partially negative, and then the hydrogens are going to be partially positive. because the oxygen is gonna pull all the electrons towards it, and it's sharing unequally because of that. So I'm saying a lot here. This is a lot, I feel like, to kind of learn it, you know, especially 2-hour delay, short class, but this is everything you need to know about polar and nonpolar. All right, so we only have maybe like a minute, so I think we'll stop here. Tomorrow we'll go over the homework that was due today. I'll review this again tomorrow, and then you'll have a worksheet practicing this stuff due Monday. I know that's not fun over the weekend, but it is what it is.